by Public Enemy. Group from the late 80s. Chuck D is the main rapper. Flava Flav was the hype man. If you heard the news yesterday, Flava Flav and Chuck D finally split. Flava Flav wasn't always with the picture politically. And so the doing crack and all the other stuff was kind of like the final straw, and then yesterday was the final straw. So sorry, Flava Flav.
Is there like no front page or something?
It's still be added onto your old one, bud. All right. My voice is better, but not great. And I will have grades in tonight, as promised.
Wait, you will?
Yeah, right.
So I can still turn some in?
I
need to figure out.
Ellie. Yeah.
When can I come in to do my 2 tests?
Whenever you want. I'll be here every day after school and
I will
before.
review for 1 more day.
Right, that's fine. I'll be here. I'll be here today too.
Can I come in before school?
Sure. What time do you want to be here before school? Because I'm here at 7:30 almost every day, guaranteed. Is that fine?
Yeah.
Okay, yeah, then just show up.
Yeah, he has it on his desk.
Yeah. All right.
The color papers.
Yep, that's right.
Or
So, what did you wonder about this question? Well, it wasn't really a question, about this warm-up.
I put, if they all are even numbers equal 100, what are the possible combinations?
Okay, so Luke went about it in a possible combinations thing. Did anybody wonder if there's only one combination?
I didn't understand it.
Well, we had a bunch of different cups, right? We had like an orange cup at the top, 2 blue cups, and then what was the other color? Purple, pink. We had something like this, right? And they said that there are 16 cubes total underneath these cups. Yep, and each color has the same number of cubes underneath it, right? So Luke was wondering about combinations, right? How many possible combinations are there? Are there infinite? Are there a certain amount? Is there only one combination that works? What do you think? Yeah. Okay, what do you think? Wait, it's not even this? Oh, then hold off, man. All right.
This goes to the Cevians proof.
Yeah. You have 2 page 8s now. You can either replace your old page 8 where we wrote stuff on it, or you can just keep it on there. Doesn't matter. Doesn't matter. Well, one way that I looked at this problem, same number of cubes underneath each of these, right? Same number of cubes underneath here. Oh, and I bought more pens. They'll be here tomorrow. Thank you. They're my passes in their brains. So, what we have here is an algebra equation, one way of looking at it.
It's too good for
Hey, get that.
So one way of looking at it is like this. Right, you have 3 of these amounts, right? And 2 of these amounts and 1 of those amounts. Did anybody try to solve and figure out what's what? Yeah, no, what'd you do? Okay, well, what are your thoughts? What is it?
triangle similarity. Yeah.
You can put it back there. I'll decide whether I want to grade it or not. The more late grades I grade, the further it puts back people who actually turn stuff on time. If I get to it, I get to it. If I don't before the end of the quarter, sorry, bud.
I kind of just checked stuff.
Okay, so what did you guess?
Well, I kind of forgot about. I put 1 in the top one, then 3 in the bottom.
Okay, 1 and then 3 here,
Yeah, and 3 in the other one.
and 3 in there. So x and y could, if x and y could be the same, one combination would be 1, 3, 3, 3, 3, 3. That's 5 3s, so that's 15, and then 1 makes 16, right? Another combination would be to put all 1s in the bottom, right? Here, here, and here. And then you'd have 5 with 11 left over, right?
You could do 2
So there are lots of possible combinations. More if you're allowed to have x equal y or y equals z, right? Or x equals z. So if you know from algebra, or if we look at algebraically, this is one equation with three different variables. Now equations we can call restrictions, right? Any numbers can be in here as long as there's two y's, three x's, one z, and they all add up to 16, right? It's a restriction on our possible answers, right? They all have to add up to 16. There has to be three x's, two y's, and one z. You can look at this as restriction. So if there's one restriction, but three variables, there's going to be infinitely many solutions. Always. Always. If the number of restrictions matches the number of variables, like if I had two more equations down here with x, y, and z in them, then the number of equations would match the number of variables, meaning the number of restrictions matches the number of variables, which means that there would be one solution likely. So you guys might remember from algebra when you had something like this, right? Now, with just this guy, infinitely many solutions, right? 1 and 1 work for x and y. You could also do 2 for x and a third for y, and that would work, right? There's infinitely many solutions. Because the idea here is that this represents a line, right? And all of the points on it would be solutions to this equation. And how many points are on a line? Infinitely many, right? Now if I've got another equation like this, and I say that those x's are the same as these x's, these y's are the same as these y's, right? It's not two different equations on two different days. They're related. Then I have two equations, right? And that means I have two lines. And two lines can intersect at one point and have one solution. Two lines can never intersect, which means they'd have no solution, right, where they cross over. And they can have be the same line, which means they intersect constantly, right? Infinitely many solutions, right? But you're never able to have just one solution if you only have one equation, right? Because you'd have infinitely many points on one line. But two lines gives you the possibility of one specific solution. Here, we've got three-dimensional line, essentially is what's going on here. It's got three different dimensions to it, x, a y, and a z. And so lines in three dimensions, most of the time, it's going to be very difficult for the all to be concurrent, right? We've talked about that in geometry. And so here, the odds are that there's no solution or infinitely many. If we have two other three-dimensional lines, and we say they're all going to be together, the odds of them all intersecting at one point is pretty rare, but can happen. So you need the same number of variables equal to the number of equations you have to have the chance of the same solution. We're going to mess with this more tomorrow and work with moving stuff around through circles, do some cool number theory stuff. Put that away for now. All right. Get out your packet. We're going to start on page 8, even though we've already done page 8 in your packet. Cevians, yep. We're just adding on. That's all. So we've already done page 8. Now I just took away the lines. I wanted to review with you guys with this. We did or did not, sort of, right? I said you guys could prove it on your own. I'm giving you a new one. Now remember, on Friday, we learned about triangle angle bisector theorem. I'll zoom in. That's my shorthand for triangle angle bisector. I drew a triangle with an angle bisector, right? So triangle angle bisector theorem says that if you have a triangle with an angle bisector, right, then you know that the sides of the angle that you bisected will be proportional to their bases. So what this implies is that x over y will equal a over b, right? And now I'm in much better health to go through this proof with you guys today. So we're going to use this triangle angle bisector theorem to prove that angle bisectors are always concurrent in a triangle. Do you guys remember this from Friday? Right? X over y equals a over b. We proved that by triangle angle bisector theorem. We drew out that extra parallel line, got the extra triangle. Turned out it was isosceles. Basically, it's page 7, right? So this theorem is true. We just proved it. We can use it now, right? It's kind of like one of our lemmas, right? And by the way, there are a lot of mistakes in this packet. One of them is that lemma is spelled with 2 M's. Sorry, guys. So, here's what we're going to do. We're given a triangle. Prove that the angle bisectors are concurrent. This is page 8, the new page 8, right?
What was that theorem you put up?
The theorem was angle bisector, or triangle angle bisector theorem. That's my shorthand for it. So triangle angle bisector theorem.
Wait,
Angle bisector theorem. So if we have an angle bisector in a triangle, then we know that the sides of the angle we bisected are going to be proportional to the bases here. Cool?
Could you say like tab theorem or something? I don't know.
Ooh, triangle angle bisector theorem? I like it. Sure, whatever you want. Tab. Like the soda from the 80s. All right. So, let's use this. So, we're given a triangle, and we're going to prove that its angle bisectors are concurrent. So, first thing, we need to add some angle bisectors to this triangle. So, let's do from C down to here. Let's do it in black. CD exist, and let CD bisect angle what? What angle would that be if we draw here to here? ACB. We should also say that ADB, we should let that exist. Now remember, if two line segments share a letter, that means that's where they intersect, right? That makes sense? Right? So let these guys exist, and let CD bisect ACB. So we're going to say let this be true. Right? Every angle has a bisector. Let's just draw one in, right? Cool. We're going to do the same thing again, but let's do it for this angle. Let's call AE. We're going to say let AE also exist, and let it be an angle bisector. So let AE and BEC, right? Those two lines exist, and let AE bisect. What angle is AE bisecting? What angle does AE bisect? CAB, yep, or BAC, doesn't matter. Now these two guys definitely intersect at a point. So if you want, you can say also let AGE and CGD exist, right? Now notice this is just like the triangle that I gave you the other day when we attempted this one, right? We talked about it real quickly. I just left out one of the angle bisectors. Can I what?
Can you? Yeah, thank you.
Cool. So, we're going to prove that these angle bisectors are concurrent. And again, we know these two are, right? Two lines will intersect at some point. The question is, will this last angle bisector that I draw in, will it go through point G? So here's what we're going to do. Let's, yeah, we'll just do it without little letters. So by tab theorem, triangle angle bisector theorem, right? Triangle angle bisector theorem. We know that AC over BC should equal what over what? Look up here if you're confused. Instead of using X, Y, and A and B, I'm using AC and BC. AC is going to go with what, and BC is going to go with what? Go ahead, Zayden. AD and BD. Is everybody cool with that? These sides of the angle that we bisected are going to go with the bases we created. Cool. And then we also know by the same theorem that these two sides, AC and AB, will go with what? AC and AB will go with anybody. BE. Now remember, AC we did first. So that's going to go with EC, or CE. And AB we wrote on the bottom. So that's going to go with BE. Right? Cool. So what we want to prove is that the ratio of these two, multiplied by the ratio of these two, multiplied by the ratio of what these will be in a second, is going to equal 1. And once we have that, we can use Ceva's theorem's converse. So let's draw in another angle bisector. Now again, we don't know it goes through G, so I'm going to purposely just kind of draw it not through G. Let's call this BF. Let these guys exist. Let BF and AFC exist. And let BF bisect angle ABC. So we've got our 3 angle bisectors, 2 of which we know go together, right? And the last one, we don't know that it necessarily goes into G, right? We're going to prove that it does go through G. But we're not sure yet. I'm going to zoom out. So if this is an angle bisector, does an angle bisector theorem apply? Triangle angle bisector theorem, tab, right? So we can say by tab. All right, now you help me with this one. We bisected this angle. What are our sides of that angle? AB. And what's the other side? Somebody else answer. BC or CB, right? And they're going to go with, AB is going to go with what? What's going to go here? AF, this bit, right? The base. The sides of the angle will go with the bases we created, right? So AF, and what's the other one? BC and CF. Yep. Cool. Cool. So Ceva's theorem says that if we take all these little bases, right, and we divide them by each other and then multiply together, we should get 1, right? And if that's true, by the converse, then they should be concurrent. So we're going to find out what does happen when we multiply AD by BD. I'm sorry, AD over BD times BE over EC times CF over AF. We're going to find out what happens. So let's find out what happens. AD over BD times, right? Guys, I'm setting up Ceva's theorem essentially. Does everybody see that? All the bases, right? So I've got AD over BD times, what are these two guys? All right, either get good or stop. Like, it wouldn't be a big deal if you made it in every time, but it's way more of a distraction than you just getting up and dropping it in. Because you missed. Who else would have missed? BE, and then what's the other side? CE, right? Times. Again, we just go around the triangle, right? So I've gone AD, BD over times BE over EC times, what's next? Nope, what's that? Oh, CF, yep, CF. Over, what's this? AF, yep. Once you pick the order that you're going, clockwise or counterclockwise, just keep going in that direction. That's how Ceva's works, right? A, B, C, D, E, F, right? Mm-hmm. Now, what does this equal? If it equals 1, then we can use Ceva's theorem's converse, right? And then they must be concurrent. Well, AD over BD, what did we say that equals earlier?
AC over BC.
Very good. So let's substitute that. Times. Daniel, what's BE over CE equal? What did we figure that out earlier?
B over CE?
Yep, that's kind of a tricky one.
Why don't you give it to me? Oh, AC, AB.
Yep, so BE over CE we did figure out, right? We just got to flip it. It's AB over AC. Are you guys seeing where this is going? Look here. Are you seeing where this is going? Things are going to cancel, right? We're going to get ones, right? And that's what we want. Lastly, CF over AF. We said that CF over AF would have been what? BC over AB, right? Now, you could have put in little letters here, like little a, little b, little c, et cetera, right? I just used the big ones. It's up to you. The triangle is blank. How you do it is up to you. And so now, we know this. What's AC divided by AC? Try it again. Any number divided by itself is 1. What's AB divided by AB? 1. And what's BC divided by BC? So we've proven that all of this equals 1. Now, if we have the bases like these little segments of the triangle, right, that are made by these Cevians, if they all multiply, if their ratios all multiply to 1, then by Ceva's theorem converse, right, they must be concurrent. So that's what we're going to say next. By Ceva's theorem converse, we know that AE, CD, and BF are concurrent. Therefore, by definition, angle bisectors of triangle ABC are concurrent. I'll zoom in on that last part. So Ceva's theorem's converse says, look, if those segments that we divide up the triangle into, the sides, right, if their ratios all multiply to 1, then those Cevians must have been concurrent, right? So we showed they all multiply to 1. So by the converse, they're concurrent. And what are those segments? What are AE, CD, and BF? They're angle bisectors, right? So if these guys are concurrent, then the angle bisectors are concurrent because they're one and the same, right? Those are angle bisectors.
You could graduate all the way to the super straight bodies.
So most of the work for this proof was drawing in the angle bisectors yourself. I just want to show you that on the quiz on Friday, you're going to have to draw in the angle bisectors yourself. So you're going to need to say stuff like this, like let this exist and let it bisect that, right? Let this exist and let it bisect that, et cetera, et cetera. Now, it's important to show this part. I think most of you are going to forget this. That these guys already intersect at G. That's important. We can conclude that two lines are going to intersect, right? They're going to intersect at some point. Those lines aren't parallel, right? Because these angles could be different, so we can assume that they're going to intersect at some point. They're inside the triangle. So if they intersect at one point, the question is, does this last guy intersect there? So you need to include that the first two do. The question is, does the last guy do, right? Cool. Basically, the idea is draw on your angle bisectors. Find out what they equal, right? These segments. AD over BD is going to go with AC over BC by angle bisector theorem, right? Tab theorem. Yes, that's fine. Et cetera, et cetera. So first we use this to find out what these A and B are going to equal, right? X over Y, and we do that for all the sides. So we get all this. And then we just set up the equation, right? What happens when we multiply these? Do we get 1? Yeah, we do. So by Ceva's theorem converse, they're concurrent.
What's the definition of Ceva's theorem? I won't get it.
So Cevians, that's a definition, right? A Cevian is anything from a vertex to the opposite side of a triangle, right? Ceva's theorem says that if you have all of these guys, this over this, times this over this, times this over this, and they equal 1, right? Then these guys are concurrent. That's the converse. Ceva's theorem states that if they're concurrent, then this will all equal 1, right? That's the difference. So we're using the converse mostly. You'll have to prove one of them at least on the quiz, right? Ceva's theorem or the converse. But we're going to use the converse most in our proofs, right? To prove things concurrent. Cool? That's the hardest one we're doing today. That's one we already did. Are we feeling okay about that? Not at all? First off, angle bisectors.
Like the first part, like the first line.
Okay.
Give it a solid 15%.
So again, feeling around 50 is okay. So if we have an angle bisector, all right, so those of you that aren't getting it, that just said you weren't, how about you look up here? No student is too dumb to learn this material, but some of you are too stupid to. Do you understand the difference there? Stupid is you make dumb choices, right? Maybe I should rephrase that. No student is too stupid to learn this, but plenty of you are too dumb to. Okay? If you look up here, you might help. Third hour, I'm concerned with you most out of all my classes. I really am. For this quiz on Friday. So, here's the logic. We know this to be true. If we bisect an angle, let me zoom in. If we bisect an angle, then we know the sides of that angle will be proportional to the bases. You with me? So that means this is an angle bisector. So the sides should be proportional to the bases. That's what I wrote here. Same thing here. The sides of this guy should be proportional to the bases. That's what I wrote here. I did the same thing here. The sides of this guy should be proportional to the bases. That's what I wrote here. Now Ceva's theorem says that, or Ceva's theorem's converse says if I can multiply these guys and these guys and these guys all up like this, and they equal 1, then they must be concurrent. So what I did is I said, well, what happens when I multiply these guys? I did AD over BD times BE over EC times CF over AF. And I said, well, what does that equal? Well, I know AD over BD is this, right? And I know BE and CE get me this. And I know CF and AF get me this. And then I notice things cancel, right? Because when we divide, we get 1. So yeah, that does equal 1. And if it does, by Ceva's theorem's converse, they must have been concurrent. So step 1, get all your equals together, right? And you're going to do that by using tab theorem, or triangle angle bisector theorem, this guy. Then after you do that, tell me what these guys all multiply to be. This over this, times this over this, times this over this. What do they multiply to be? Turns out 1, right? So that means this converse must be true, which means they're concurrent, and you're done. Are you feeling about 50? No? I gotta move on if you want to see me after school. That's fine. I need a little bit more effort from you guys in class, though. I know. All right, much easier one. Yes?
So is this test just going to be on Ceva's theorem?
This entire packet. So it's going to have the lemmas in it. It's going to have Ceva's theorem and its converse. It's going to have any of the angle bisector theorem and stuff, right? Triangle angle bisector theorem. And then it's going to be proving these guys concurrent. Okay? Now, am I going to have all those proofs in there? No, we don't have enough time. But I'm going to have at least 1 or 2 from each of those. Okay? So will I give you Ceva's theorem and Ceva's theorem converse to prove? No. I'll give you 1.
Can I go to nurse?
Yes, you may. All right, so now we've got a triangle. We're on page 9. We're going to prove that medians are concurrent. This is a much easier proof. So, what's a median? Yeah. Yes, so it goes from vertex to a midpoint, right? So let's create some medians here. Let's go from C to D. Let's say let CD, and it intersects with ADB, right? And then if you want, you can write let D be the midpoint, or you can write let AD be congruent to BD. That's what I'm going to write. Right, every segment has a midpoint, so I said let D be it, basically, right? And I said I'm going to draw a line from C to D. And I'm going to do that same thing for A to the opposite side here. So I'll call that AE. And I'm going to say let BE be congruent to CE. Cool with that? I'm going to draw another line. And again, I'm not going to have them intersect. We know they will, right? But that's what we're trying to prove. So what I'm going to do is I'm going to do something like this. And say that that's the median. We'll call that BF. AFC is what we want. Whoops. And we're going to let AF be congruent to CF. So basically we just constructed medians, right? That's cool. Every line has a midpoint. I'm saying I'm going to draw a line that goes from the midpoint to the vertex. Now the question is, do all those lines intersect, right? Are they concurrent? And that's what we're going to prove. Any idea how we might do it? I'll give you a hint. We're going to need to prove that this divided by this times this divided by this times this divided by this is 1, right? And once we've proven it's 1, by Ceva's theorem's converse, they must be concurrent.
You alright?
So we just drew in a bunch of medians. Noah? We just drew in a bunch of medians. Okay? That's all. We're trying to prove that medians are concurrent.
Oh, is that like the...
Right, we're on page 9.
Oh, makes sense.
So here's the deal. We're basically done. If Ceva's theorem's converse is something we can use, which we're hoping we can, because that's how we prove concurrency, right? Then AD over BD, we need to figure out what that is times BE over EC and CF over AF, right? We need to figure out what that equals.
So we just do the same thing like 3 times.
So let's set it up. AD over BD times BE over CE times CF over AF. Now, what do we know that equals, Zayden?
We know it equals 1
How?
because AD is equal to BD, so it's going to be a number over itself, and then for each of those.
Do you see how AD and BD are the same thing, guys? Right? So that's going to equal, let's do substitution. Let's, instead of writing BD down here, what can I write instead? What can I write instead of BD by substitution?
Wait, what?
Instead of B.
I can write AD, right? They're congruent. They're the same thing. So I'm going to write AD.
Oh, because then you can combine.
Yep. And instead of writing CE, what can I write? I can write BE, right? And instead of writing AF, I can write CF. Now, does this equal 1?
Yes.
So all I did is I set it up, right? This times this, this times this, this times this, right? Cool. And I said, well, that's the same thing as AD over AD because BD and AD are the same, right? So when I do AD divided by AD, what do I get? What do I get? 1 times 1 times 1. So, what am I going to use now to prove that they're concurrent? Now that I know that these all multiply to 1.
Ceva's theorem.
Yep, Ceva's theorem's converse. I know that the lines that I drew, AE, CD, and BF, are concurrent. Therefore, by definition, medians of ABC, triangle ABC, are concurrent. And that's it. Right? Our journey, like our job for this, is to figure out these segments, when I put them in ratio and multiply them together, do they equal 1? If they do, then I can use Ceva's theorem converse and I win. The question is, how do we get to prove those are going to equal 1, right? For here, it was really easy. This divided by this is going to be 1. This divided by this is 1. This divided by this will be 1. Right? They're the same thing. So when you multiply them together, of course you'll get 1. How do we feel about that one?
That's pretty nice. I got it. Yeah.
Yeah? Jess, how you feeling? Yeah? Nancy, you catching up? Yeah? I know you're gone, but you feel good about this or no? Yeah? Okay. Evan, how is it? Bad? We created all this stuff. We get up to there? Okay? So I need to prove. My whole goal is to prove that these are concurrent, right? And in order to do that, I'm going to use Ceva's theorem's converse, which says that if all of these multiply to 1, then they're concurrent. So the question is, what do all those multiply to be, right? So I set that up. Are you with me up to there? AD over BD. Well, I know AD over BD is going to be the same thing as AD over AD. Evan? Because AD and BD are the same thing. So I rewrote it as AD over AD. BE over CE, well, they're the same thing. So I rewrote it as BE over BE, right? And since this is the same, I can rewrite that as CF over CF. Anything divided by itself is 1, right? Anything divided by itself is 1. Anything divided by itself is 1. And 1 times 1 times 1 is 1. So if this does equal 1 by Ceva's theorem's converse, they were concurrent. You feeling okay with that? All right. Let's take a look at 10. We've got a new theorem that we've got to learn before we can prove perpendicular bisectors are concurrent. So perpendicular bisector theorem. This is kind of a lemma in order to get into prove that perpendicular bisectors will be concurrent. If a point is on the perpendicular bisector of a segment, observe. Is that a perpendicular bisector? How do you know it's a perpendicular bisector? It's perpendicular and it bisects this side, right? Is the point on it? Yes. So then that point must be equidistant from the endpoints of the segment. So if we have this, we get this. It's the same distance from the endpoints. We have a quiz Friday over all of this stuff. It is a super quiz. Instead of failing it, try paying attention in class first instead of making me come in after school and teach you then. That'd be my advice. Because that's when I get paid, like now. And I don't mind you coming in after school. In fact, I want you to. My favorite part of my job is teaching kids. But I'd like to do that when I get paid too. So morons over here that are doing stuff other than math, I guarantee that other class you can BS a lot easier than this one. So at least be smart enough to know which class you should BS and which one you shouldn't. Right? That's all I'm asking. That's all I'm asking. You know which class you can BS. It's not this one. All right, so if we know this, we get this. Why is this true? And that goes for people over here too. How do we know that this gets us this always? How would we prove that? Zayden.
You can draw those triangles but not say that they're the same yet. Then you could do shared side, you'll get that side, then the angle, then the other side, and you're going to be able to prove them congruent and by CSP.
Yeah, basically. So the big key here is that, look, if I were to draw in here to here, and I want to prove that D is equidistant to both A and C, what I really want to prove is that these segments are the same, right? Well, if I draw those segments in, don't I have two triangles that are congruent? How do I know those two triangles are congruent? Side angle side. So by side angle side, they're congruent, right? So I'm going to say let AD CD exist, right? That's what I drew into my triangle, or this diagram, right? And then how did I know BD was congruent to itself? Yep, by shared side, BD is congruent to itself. And now how do I prove those two triangles congruent? What do we say? by side angle side. Triangle ABD must be congruent to triangle CBD. Nice. Now, how do I prove these two blue lines are congruent? What do I do next? This is a problem like we did like 4 or 5 weeks ago, basically. By CCP, right? Corresponding congruent parts. We know that AD, does everybody see that? AD should go with CD. And they're not similar. We said they're congruent, right? So their segments will be congruent. So if AD and CD are the same length, by definition, D is equidistant from A and C. All right. Tomorrow we'll prove the converse of this. I'm going to give you this. And then we'll prove perpendicular bisectors are concurrent and orthogonals are concurrent. Let me reiterate. Sit down. Class is over. You need to bring your A game this week. If you don't, there is no hope for you on this quiz. If you do, there's a lot of hope. Quarter ends in 2 weeks, and grades will be locked. Since you guys are too young to be mature enough to take care of your crap, I will be taking your home. Again, all I'm saying is you guys are smart enough to be able to play the game. I'm not saying you have to pass all quiz, but you at least got to be out. It's annoying.